So you think that you will move from more generalized to like more specialized because there are a lot of like demands in different industries. So, any other thoughts? Like how much progress will they have? Okay, if there's okay, I can share a little bit about my prediction. First of all, I think it's really cool, the humanoid industry. I think it's really like revolutionized and really pushed the boundary of our robotics industry. But one thing is that I think although there will be like really cool demos, I think sorry, this does not work again. I believe that there will be tons of engineering works for us to customize for each applications. So here's an example. So this is warehouse automation. These are people who are trying to pack our packages, those Amazon packages. So you can see how complex these motions are, like manipulating these bubbles, manipulating these shapes. You can see a lot of huge variation in these motions, and thinking about that, we can have, I mean, hundreds of thousands of objects in the inventory, and each time their arrangement could be different. So this is actually a very challenging task, and also a lot of long horizon decision making in these fine motions. So it will be like really, and imagine that there will be hundreds of thousands of different manual processes in many different industries. So I think what is shown here really revealed a gap that dexterity is actually challenging for our current AIs, even though they have demonstrated this great potential in language and perception intelligence. Our current AI system does not have the motion intelligence to really automate these manual tasks. So this actually has gotten more and more attention. In this book, it says that AI will likely to still struggle to master, even in 2041, dexterity. And in this report from Oxford, manual dexterity is considered as one of the 3 bottlenecks to computerization. So what is dexterity? So in our dictionary definition, dexterity is the ability to use the hands to skillfully in doing something. This is obviously very broad and very vague. So in our robotics community, dexterity is defined as multiple manipulators or fingers to cooperate to grasp or manipulate objects. So I think there's still like some gap to the human level dexterity we have just seen in that application. I really like this definition from psychology that dexterity is the ability to find a motor solution for any external situation, that is to adequately solve any emergent motor problem. So I really like the emphasis that they are putting emphasis on this emergent motor problem that, I mean, anything could happen during our daily manipulation, and it's necessary for us to find this emergent motor solution. So to me, dexterity is the autonomy in manipulation. So consider an analogy to autonomous driving, of which its goal is to fully automate driving in the cars, where it could encounter a lot of different emergent road problems. The goal for robot dexterity is this full autonomy in manipulation. But one thing is that the autonomy in manipulation is going to be much more complex than autonomous driving, because thinking about our hands and the arm, so the action space is actually much higher dimensional compared to cars. And also, in manipulation, we need to physically interact with the objects. In comparison, in autonomous driving, there's no need to like physically interact with the like pedestrian, for example. So, yeah. So, but the potential of the robot dexterity is not just about households. It's also about to revolutionize many different industries. Like there are a lot of manual processes in manufacturing, construction, warehouse, space operation, and recycling, and so on. So, but right now, all these industries are having some labor shortage. So in this talk, I'll provide some new perspective in robot dexterity. And then hopefully after this talk, you'll be able to see more connections among these very similar different tasks. So let's look into a little bit more about human manipulation, human dexterity. So here you can see that this person is actually very reactive, very fast, and very robust in manipulating these tiny objects. And so this is just a person trying to pick up items in the grocery store. You can see for these simple tasks, there are a lot of complex hand motions, a lot of complex object, hand, and environment interactions. This is just a single task. And this is the warehouse automation problem we have just seen. And looking at this person trying to assemble these poker cards, can you name and count all the maneuvers this person used? And you can see it's really very fast, but extremely robust, these motions. And finally, so here you can see this person inside the excavator is using some very smart motion strategies to use this very simple and bulky excavator to do this very complex task of replacing a pipe. So we can see a lot of complex interactions, complex maneuvers, and seamless synergy in human manipulation. So in our robotics research, we only understand a very small part of dexterity. A lot of times we assume that we need to have a dexterous human-like hand, robot hands, in order to have dexterity. And so I believe most of you have seen the OpenAI Rubik's Cube thing. So a lot of us believe that dexterity is about manipulating things within the hand. But if we look at these examples of human manipulation, we can see that, so from this excavator example, it's using very simple tool to do very complex tasks. So dexterity is more from the intelligence inside the excavator, which is the human mind. And from this packing example, we can see that it's not just about reorienting things within the hand. There's must be more complex, smart strategies rather than in-hand reorientation. So how do we move from our current understanding to this more general dexterity? So I think it's important for us to answer more fundamental questions about dexterity. So from my research, I'll provide some answers to the three questions below. If it's not just about dexterous hands, then what kinds of robot can have dexterity? And if it's more than in-hand manipulation, what else should be considered beyond this robot-object interactions? And also to capture the complexity of dexterity, what skills will robots need? And finally, motivated by the answers to the three questions, I'll discuss more about our path towards general dexterity. Our first question, I think the question is not as simple as it seems. I think it really encouraged us to reflect what dexterity is truly about. So dexterity is not just limited to anthropomorphic hands. Even very simple end effectors can also have dexterity, like shown here from this excavator, from just very simple tweezers, or just from this chopsticks. So you may ask this question, why do we want robot dexterity beyond anthropomorphic hands? Why can't we just build human-like hands and let it do everything in different industries and in our households? I think the first point is that it's just like why we invent tools. We want to extend the physical capabilities of robots. We want the robot manipulation to have higher precision, to do heavy-duty tasks, or to even have better performance in scenarios that's not naturally suitable for human hands. And we probably also want better cost efficiency. So human-like robot hands, they are extremely expensive, very hard to maintain. But in industry, what we're using are suction cups or like these very cheap pneumatic robot hands. Imagine how much we can do by having dexterity in these simple end effectors, and as well as how much we can save. So in my PhD research, I have demonstrated dexterity in several different robots: a vacuum suction cup, a rubber ball on a rod, a parallel gripper, a 4 degree of freedom direct drive hand. So this hand, it has 2 fingers. Each finger can move in X and Y. And also an array of delta robots. So this is just an array of very small robots, and each robot can move in X, Y, Z, but their range of motion are very small, so they need to collaborate together to do any manipulation. So let's push things to the extreme and say that, okay, the simplest robot end effector can have dexterity. So this is a rubber ball on the rod, so it has 0 degree of freedom. But you can see that I've demonstrated that it also can have some dexterity by pushing something onto the wall or getting this object through an obstacle. And the next thing is that if we are adding some passive degree of freedom on the bellows and also some vacuum suction force, we got a simplest robot gripper that is mostly used for pick and place in the industry. But here I show that it can do controlled reorientation. So in fact, for example, this object is too heavy to be picked up, but we can still be able to tilt the block without picking it up with the help of the table contacts. So it's really extending the robot's capability. And also I have developed an optimal control pipeline where we can intentionally use the finger deformation to minimize the robot motions so that the robot will not go out of its workspace. So this is the dexterity for the simplest robot gripper, and we can imagine that it can have more applications, future applications in industries like warehouse automation, that we can, for example, move and pivot things around in order to pack things. And obviously, a slightly more complex robot hands can also have dexterity. So this is the direct drive hand. This object is not directly cannot be directly picked up because of the occlusion from the environment. But it can still have some dexterous strategies by, for example, first pivoting this object and then do some dexterous finger maneuvers to grasp the object. And this is just a simple parallel jaw gripper. You can see this shelf environment is pretty occluded, but it's able to figure out a sequence of motions in order to get the object to its goalposts. And also these small delta robots, they are able to collaborate together in order to reorient an object. And just to mention that, I'm using the same algorithms to automatically generate the motions for these different robots, and I'll cover more technical details in question 3. Okay, so coming back to our question, what robots can have dexterity? So I think my belief is that dexterity should be the motion intelligence that in the future that all of our robots should have. So I'm putting a question mark here is because that obviously we cannot have any rigorous proof about that, but I want to use this as a thinking point to think that robot dexterity should be greater than human hand dexterity. It can be inspired, but go beyond their human hand capability. Okay, so if we want to enable all robots to have dexterity, then it must not be just about manipulating things within the hand, doing in-hand reorientation. then what should be considered beyond robot-object interactions? So here's a question for you. What else do you think is manipulating the object in the scene? So yes, that's correct. So it is the table and also the fixed green block to the table. So we can call this the environment. So it is actually very necessary for us to not just think about in-hand manipulation, but also consider the object-environment interaction in manipulation. So why is that? The first thing is that the environment is the blocker for the robot. So you can see that if the robot wants to grasp this block, it is actually occluded by this green block and this table, so it cannot achieve a direct grasp. And the environment can also be a helper. So yeah, so for the blocker, the environment is then the obstacle for the robot. But for the helper, in terms of that, you can see that the robot can actually use the environment in order to pivot this object, in order to achieve more dexterous, more clever motions to grasp the object. So here are some more examples of this direct drive hand using the environment to achieve previously unachievable goals. So for example, this bookshelf is obviously occluded by the bookshelf, but it was able to figure out the pivot motion on the bookshelf and then rest it on the bookshelf and then grasp it. So you can see it's really using the environment. And also pick up the card by sliding the object on the table first. And then this pinch grasp by first pivoting this object in order to grasp it on its short edges. So to answer our second question, it is really important for us to consider the environment contact interactions of the object in order to achieve more general dexterous manipulation that's more than in-hand manipulation. Okay, so considering all these complex contact interactions and all these different robots, what skills will our robots need in order to capture dexterity, in order to capture that complexity? So our first question is that, can dexterity be fully captured by predefined skills? So a lot of our robotics research, we consider that we can predefine different skills. They can be, for example, hard-coded. They can also be learned from our observation of different trajectory shapes. And normally we can sequence them together in order to achieve a task. I think it's completely fine for many different tasks, but can that capture dexterity? Okay, so we have several options. The first option is that we can probably predefine some high-level skills like pick and place and push and I don't know, pull, things like that. But here I'm going to show some videos for the picking skill. So you can see that it's very, very different. The trajectory for each picking skill is going to be very different. And the contact interaction is also very different. So if we're defining high-level skills for dexterity, we still need to plan these dexterous motions within each skill, which actually does not fundamentally solve our problem. And our second option, let me just stop this video, is that maybe we can predefine low-level skills. These low-level skills can be, for example, have similarity in trajectory shapes, or even one low-level skill, they can have continuous constraint dynamics. So if we know their dynamic equation, we can sequence these different skills, and we can easily have better control for that. So, so here's a table for all these low-level skills for gorilla thistle eating. So it's just one task, but the anthropologist has observed that there are like about 121 skills for these simple tasks. And for gorilla manipulation, I think in total, they have observed over 300 skills. So imagine that for more complex dexterous human manipulation or the requirements of that kind of daily manipulation, will these skills be innumerable? So why is that? Why is this so complex? So I think part of the complexity is really from context. And context, you know, how the hand would interact with the object, how the object would interact with the environment are very essential in manipulation. So if you look at these examples, you can see there are a lot of changes of context. The object environment context, the hand object context. And you can see they are actually quite complex. And the changes in these like motion trajectories and the changes in the system dynamics are all caused by the changes of context. And imagine there are so many different ways for the hand, for the object and the environment to make contact with each other. So you can see like there's perhaps this like combinatorial explosion of these different ways of contacts. And that's causing these like seemingly numerous low-level skills we have seen. So here is something that help us understand this more mathematically. I think something is blocking the title. Let me just, oops. Sorry, I think I cannot close that. Yeah, so this is the simple 2D example. It's basically showing the object configuration space partitioned by context. So the object is basically the red triangle, and the environment is this blue polygon. And this is showing the object configuration space x, y, theta for the triangle. And you can see this space is partitioned by this by how the object in contact with the environment. So basically, each facets or each lines you see here, they correspond to a different way that the object can make contact with the environment. And so basically, each facet we can write down a continuous contact dynamics for the system, and each low-level skills would live on a facet. So you can imagine that it's already very complex for this simple 2D example, and for like real world 3D objects, and considering more complex environment, it is a lot of times impractical for us to explicitly draw this shape. So contacts really are giving us a lot of headaches. But a nice thing is that a challenge could also be an opportunity. What I've done in those algorithms is that I leverage contacts to automatically generate new skills. So how do we do that? A one-sentence summarization is that we use contact modes as auto-generated low-level skills. So basically, I'll explain what contact modes are in a second. But basically, by using these contact modes, we're basically looking at the local information for these small facets, and then use that local information to guide the generation of different skills. So what is a contact mode? A contact mode basically describes the transition of the contact states in the system. So for example, we have two contacts here marked by the black dots. Each contact, they can have the mode of separate, fixed, right slide, left slide. And here are some examples of the motions corresponding to different contact modes. I mean, these are not all the possible contact modes for the system, but you can see they are already can represent some like diverse motions for the object. And similarly, we can also have contact modes in 3D. It's slightly more complex But we're essentially looking at the space for the contact velocity in order to like distinguish the modes. So in this video, the purple arrow is for the contacts that are separating, and the yellow arrows are for the contacts that are maintaining. So you can see that they can actually represent pretty rich contact motions, rich object motions under different dynamics. And this is also some contact modes for the hand and the object. So how do we use them as auto-generated low-level skills? So I would explain this from the perspectives of low-level skills and how are they auto-generated. So basically, for a contact mode, if we're given a contact mode, it's very easy for us to write down the continuous constraint contact dynamics of the system. So for example, for each of these modes, we can write down their dynamics, but the dynamics across these modes, they are quite different. So if we don't know about these dynamics, it's going to be very hard for our controllers to achieve some sort of motions, or it's going to be very hard for the planner because the planner does not even know, what kind of dynamics equations are there, what kind of different combinations of modes we will have. And so this basically, we can use this if we know the continuous constraint contact dynamics. We can basically consider it as a low-level skill. And previously, people thought that contact mode enumeration, like enumerating all the kinematically feasible contact modes, is exponential to the number of contacts. But in our lab, we have shown that there's actually we develop a polynomial enumeration algorithms to basically enumerate all these feasible contact modes for the system. So it's usually for a single object in 3D, usually just require milliseconds to enumerate all the feasible contact modes for a certain state. So it's really making practical so that these contact modes, they can be automatically enumerated. And for each contact mode, we can automatically derive its contact dynamics. So it means that there's no engineering effort required to predefine different skills. It's all automatic. So it's very intuitive. It's very intuitive to use them to generate different skills. So imagine we have this current state of this object, and then we have a sample state. What we can do, the first step is going to be contact point detection. So in simulation, it will be with, like, for example, collision detection algorithms. And so in the real world, we'll probably have a camera looking at the scene and segmenting the point cloud of the scene and extract some contact points. So after we have detected these contact points, we can do our contact mode enumeration. So we'll get all these different kinematically feasible contact modes. And then for each contact mode, we can sample a feasible robot action. So in our case, it would be sample robot object contact points. So here's an example of just sampling one contact points for the right slide and right slide. So we'll do feasibility check on the sampled points, and we will see that, okay, in order to have this object to slide to the right, we have to make contacts on, for example, this area instead of this area. So we can do a force check to reject a lot of infeasible samplings. And then after that, given the robot action, we can actually do something I call projected forward integration. It's basically just about integrating the object motion as close as to the desired sampled pose as possible. So it'll be, so this is for separate, and this is for the right slide, separate, fixed, separate. So a lot of times you'll see that they cannot exactly get to the new pose, but still we can have diverse motions being generated using contact modes. So this does not only work for simple cuboid shapes, this also works for complex shapes. So the green lines here are the detected contact points. So you can see that they are quite noisy and not that accurate, but we can still use these contact points to enumerate the contact modes and use them to generate these various motions shown here. Mm-hmm. So, I mean, it really depends on the collision detection algorithm, whether the algorithm can detect contact points, right? If it can detect contact points, it can also enumerate these modes for the contact points. Yeah, so for the simulation here, I think it's a very good observation. We have the collision detection algorithms we use only works for like convex object, and they use approximations for them. And yeah. So yeah, then we can combine these contact modes with the power of search and planning. So we can combine these locally generated skills with contact modes, with a more powerful global exploration, for example, with rapidly exploring random tree. So this is basically intuitively how it works is that it can it can randomly sample a new pose in the object configuration space, and then we can use this random pose to find their nearest neighbor, and then to use these modes to generate many different skills. Some skills will be successful, some will not. But we can run this process iteratively to grow the tree and to do the planning to get the object from its start pose to the goal pose. So interestingly, that we have proved that a 2D version of this random tree algorithms is probabilistically complete in our given problem scope. It means that for our given problem scope, the probability of finding a solution of that dexterous manipulation problem will be close to 0 as time goes to infinity. So I think intuitively it means that given our problem scope, we can use these contact modes to gradually explore like the whole space of dexterous manipulation. One more thing to mention is that our problem scope is for this proof is 2D manipulation and quasi-static manipulation with rigid body, with a single rigid body as the object. And then later we can also combine, slightly improve these algorithms with something like Monte Carlo tree search, so that we can get more optimized contact sequences. I'll not cover the details for the algorithms, but basically we can have more efficient contact planning by leveraging Monte Carlo tree search for their balance of exploration and exploitation, and use prior knowledge and optimize with some reward functions. For example, we probably want less contact changes or more robust motions. So yeah, so these are all these like different tasks, including we have 2D tasks, 3D tasks, and tasks with different robots. And it's all using basically the same algorithms with contact modes. Just one more thing to mention is that we are looking at quasi-static and quasi-dynamic tasks. So we're not really addressing dynamic manipulation yet. So the planning time is about seconds to tens of seconds, which is the state of the art. So I'm not able to like show you all the videos for these planning tasks, but then I'm gonna share with you some most interesting takeaways from my experiments. So the first thing is that although we do not have these prior information about human manipulation, these planners, they can also generate many similar strategies to human manipulation. For example, for this unpacking, a similar human manipulation is also about like sliding this object on the wall to get this object up. And also about this bookshelf problem. Yeah, so this is a similar strategy in human manipulation. So, and also like picking up a book. So like retrieve a bottle. That's the grocery experiments I've shown. Yeah, so I think it's really that that environment contact guided manipulation is actually also very common in human manipulation. And by using this information about contact modes, we can actually have the robots to leverage the environment as an effective tool for manipulation. So there's also some smart strategy that's less likely seen in human manipulation. So here's the quiz for the students. This is the upward pegging hole problem, where this is our start. This is the goal, and we don't want so the red dots are the finger contacts, and we don't want the finger contacts to collide with the hole. So what would you do? Any thoughts? Remove the hole? No, you cannot move the hole. The hole is fixed. So one thing is that if you release the finger, the peg will fall down. So how would you push that in?
Slide.
But if you slide it, let me see. If you slide it, you will lose support on this side, right? Yeah. That's
It's the side.
Yeah, bingo. So I think both of your solution is really good. It's just that our we're not tackling dynamic manipulation yet, so that this is my fault. But yeah, this is actually what the robot is doing, exactly as what you just mentioned. But clearly you can see the robot spent like 10 seconds to figure this out. So we can definitely see that this scenario is less likely seen actually in human manipulation. So even as humans, we still need some time to figure this out. What I think this is really showing is that some autonomy without the human intervention or human demonstration. Okay, so here's the pegging hole sideway problem. So you can see this time it does not need to press against the hole. It can just let it rest on the hole and on the other finger. So all these experiments you have seen, and they are all generated by using the information of contact modes. Also, there's some robustness with force and compliance control. So all these motions are executed with force and compliance control. So what is force and compliance control? So here we use hybrid force velocity control. It's basically like if you are given it contact mode, it is able to figure out which directions you want to control the velocity and which directions you want to control the forces. So in this example, you can see the object could be slightly smaller or larger, or the surface can be slightly tilted, but because we're asking the robot to maintain the force in this direction, so with these type of uncertainties, the robot is still be able to maintain its forces and also complete the motion. Yeah, so I think what is really shown here is that with this indication of contact modes, we're not only having the diversity in motion, but we can also obtain more robustness in this control by having force and compliance in our system. So this is so in this case, we are it's not like previously we have all the models. We have the robot, we have a camera observing the scene and getting partial point clouds, and then do the segmentation of the point clouds. And although you can see that it can be quite noisy and also partial information about these contact points, but we can still use that to enumerate different contact modes. And if we're giving a goalpost, and we can feed that to force and compliance control, and it can do the execution. And then from that execution, we can collect data and then learn which parameter is more likely to be successful. So basically, we have this planning, execution, learning, and planning loop. So you can see that even with this partial information, and also some uncertainty in the environment, it is still able to execute and generate different motions, diverse motions like sliding and pivoting up, and side pivot, and things like that. So I think the main takeaway is that so when we're considering the skills for dexterity, perhaps it's not just about trajectory shapes. As we can see that we use contact modes and force and compliance control, I think it would be really nice to have this information, for example, in our skill representation or in our data collection in our future work for dexterity. So it can also plan very complex robot contact changes. And if you are looking at the right, you can see because we are essentially like using contacts as an abstraction, you can see actually has no problem in sampling contacts within the object, like within the mug for this very complex object of this clamp. So coming back to our third question, what skills what do robot needs to achieve dexterity? I think, do we need predefined skills? Of course, I think we definitely need these predefined skills to, for example, make the planning time shorter, to do some tasks more easily and more smoothly. But I think it's still very important for us to be able to automatically generate these dexterous skills in order to deal with the emergent situation for dexterous manipulation. So here I show that we can generate new skills guided by contacts. I use contact modes, but if you think about contact modes, they're essentially basically a way to guide the motion generation to let our motion to generate motion that on the lower dimensional manifolds of the original search space. So if we're a broader implication of that is that, for example, for more complex objects, so right now I'm only focusing on a single rigid body, like for more complex deformable objects or like soft objects, articulated objects or multi-object, it's probably not practical to consider all these different contact modes. Can we have something similar to figure out these like lower dimensional manifolds? If we have a way to automatically identify these different modes, we can probably use very similar technique to generate dexterous skills for these different objects. And another takeaway is that I think it's really worth rethinking about the definition of robot skills, where we observe that dexterity can, very good abstractions for manipulation dexterity can be contacts, force, and compliance control. So just a review about the 3 questions we have. I believe that all robots should have dexterity. It's important to consider environment contact interactions, and also consider like automatically generate new skills by using, for example, contact informations. Okay, so next I'm going to discuss the path towards general dexterity and also a little bit about my future work. So if we believe all robots can be dexterous, I think it's a very good way for us to like inspire new opportunities for new forms of dexterity in many different industries. So personally, I'm interested in, for example, how do we move from fingertip dexterity to whole body dexterity? In human manipulation, we can have use our elbow to open the door, or when I'm like playing with this thing, I'm actually using my palm contact and the segment of my fingers. Or when we're moving a large piece of furniture, we're using our chest and our arm. So I think it will be very useful for our robots to have that type of whole body dexterity. And also inspired by these multiple delta robots, can we have multi-robot dexterity for like more general multi-robot system? And finally, we have seen that we can actually use very simple end effectors to have dexterity. Then can we have discover more dexterity from using simple tools, very simple tools. And the next thing is about how do we develop more general dexterous robot skills. So we have observed that contact-guided skills and force and compliance control, they can be very good abstractions for these skills. I think, but I think currently most of the robotics research, we're focusing on collecting trajectory data. And collecting these type of robot data, they are extremely expensive. So what I'm actually thinking is is that we can perhaps use our takeaway about context and force and compliance control to augment, for example, more efficient learning from large-scale data. And so that we can even have these skills to be generalizable across tasks and transferable across robots. Because in the planner, you obviously see that it actually doesn't really make too much difference for us to plan for different robots. So they can be very good abstractions for learning more generalizable dexterous skills. And finally, and next is that I feel like from my experience in different industries, I feel like our current robot infrastructure is actually not made for dexterity. So here in our lab, we have collaborated with a car part manufacturer. They have a lot of manual processes that still require human worker. So here's an example, it's the door latch assembly problem. So you can see that these parts are extremely small and they need to assemble these parts into this irregular shaped housing. Obviously, our current robot system cannot do that, and we are also facing very similar problem in academia. So in fact, there's a dexterity benchmark test for manipulation, but it is for human manipulation. So far, I haven't really seen any like general robot hands that is able to do these tasks. But if you know, I would really love to learn that. Yeah. So yeah, so our system is really not made for robot dexterity. So I think so this dexterous direct drive hand system, I have already demonstrated that it can do many tasks that was not shown in the previous literature. Here I'm showing that it's trying to reorient these small parts into the pose that's ready for assembly. So we haven't done the assembly yet, but it's trying to get it into the pose for assembly. So I think, yeah, in the future, I really hope, I think this is a community effort. I really hope that we can build this similar system integration for us, for our robots to do more dexterous tasks in many different industries. And finally, I think we still have very little understanding about the real dexterity. I think it's very important for us to study the real world complexity, or even study, for example, human manipulation, motor control, building benchmarks data set, and even like how do we evaluate dexterity? How do we have a formal definition about dexterity? So I think they are all very interesting problems for us. Okay, so finally, I would like to thank my collaborators for making this work possible. And thank you all for attending this talk, and I'm happy to take questions.
I have just a very good question. My first question is, spoke about dynamic manipulation. Yeah, usage of forces, for example, throw an object
Yes.
to a specific destination.
Yes.
Use of gravity to make it go to one location.
Yeah.
How much more complex or complicated would it get? Would we still use contact points?
Yeah. Okay. Do you want me to answer the first question? Yeah. So if you look at this throwing, this throwing motion, you can see that it's still like the same like dynamics in the system. The dynamics does not change. So I think really for dynamic manipulation, understanding and knowing these different contact modes are also very important. So in fact, you can actually extend the same framework I used here for quasi-static manipulation, for dynamic manipulation. The only component you need to add is add a dynamic trajectory optimization for these known contact modes. So basically, like if you have this planner, what you need to do is for the terminal node, you do a dynamic trajectory optimization to see if you can find valid dynamic trajectory plan. But I think the challenge is that running that trajectory optimization is probably going to take longer than the whole planning process for quasi-static and manipulation. But I think a good way to solve that is that if you look at the real world manipulation, it's like a mix. A lot of times it does not have to be that dynamic. So it can be like a mix of quasi-dynamic, quasi-static, and dynamic manipulation. I think probably a more efficient way is that you can switch among these different different models for manipulation and in the planner to have a mix of both. Yeah.
I've seen the trend recently. So we talked about how you're going to use sampling-based motion planning algorithms to sample specific contact points with the right actions. But I've seen a recent trend where sampling-based planners and classical-based motion planners have been replaced by diffusion models and deep learning-based techniques.
Yes.
Do you think that trend will continue even in this specific area?
Yeah, so I think that's a very good question. So basically the question is about can like diffusion, these like deep learning diffusion model replace what we have done here? My quick answer is that I don't think they will completely replace, but they can be very useful and we can integrate them. So why is that? Because so the problem is that you can think of this manipulation problem as for example, a physical agent problem, like, right? So for these manipulation processes, you still need to make longer horizon decision-making about generating these motions, switching, for example, different ways to make contacts or how the objects will make contacts. So I would consider it as the long horizon decision-making problem. But even so for these large model thing, also, I mean, in the AI, in the NLP community, they also have this problem of AI agent where they need to have the agent to physically interact, making long horizon, not physically interact, virtually interact, and making long horizon decision making. And I think in the NLP community, they also observe that this agent problem, this long horizon decision making problem is actually very challenging for these large models. Even though they have like tons of language data, they can still not have these like AI agent to make very good decision in the real world. So, but I do think these models, they can learn something that's very local. For example, I feel like they can definitely learn motions like this. So we can like learn the motions of like changing the hand contact to rotate this object. So I feel like they can definitely be very helpful in these low level. Yeah. Mm-hmm.
What is the natural way of visualizing the set of all contact modes? You're able to generate many contact modes and generate low-level skills for each one. But how should we think of the set of all possible contact modes? This is something like a tree. Each one of these contact modes is basically a submanifold. Right?
Yeah.
So you must have something to visualize the set of all contact modes.
Yeah.
Index the set. How do you index into them? How do you label these contact modes?
Yeah. So okay. So this is so the question is like, how do we visualize these different contact modes? So one thing about contact modes is that the contact modes are generated based. You can think of these contact modes, they are basically partitioning the like tangent space for these manifolds. We are essentially looking at the objects velocity space, and then we are partitioning this object's velocity space using these hyperplanes. The hyperplanes are created by those contact constraints, and we are using these hyperplanes to partition this space. So it's basically the hyperplane are all on the like across the origin of the object velocity space. So each contact mode is basically a facet of these like intersections of these the cone created by those hyperplanes. Thank you. Yeah. I haven't done any work with manipulating non-rigid body. I think this is a very good question. So if we're thinking about non-rigid body, I think probably mostly people are like separating it into two categories. One is articulated objects. They are like rigid, but they are rigid objects connected by some different kinematic joints. And the other category would be like deformable object, like cloth, or like very soft things. So I think a very I would use the broader implication from the contact modes. Basically, if you ask me to solve this problem, for example, for these articulated objects, the motion modes could be like, for example, the kinematic constraints in the system. Like for this, I don't know, for a door, the kinematic constraints is basically like a revolute joint. It's about rotating at an axis, or for these chairs, it's about rotating at some other axis. Or it could also be like for this table, the kinematic constraint is that it's always on, we can push this thing around. I think for these type of articulated objects, we can, for example, essentially use some learning algorithms or interactions to figure out what these kinematic constraints are. And for this deformable object, I think it's more complex. It's essentially about, we can also consider about this, the problem for them is that they are so high dimensional. And I think one way to reduce that complexity is that we observe these like lower dimensional space to manipulate these objects. For example, like a cloth, it's normally we only care about like folding them or like flattening them. So maybe we can use this task-specific thing to figure out these like different motion modes for these deformable objects. Yeah, thank you.
We're running a little out of time. There's a reception now. I mean, not reception, but we have around to ask questions to the speaker. But otherwise, let's thank Xianyi again.
Thank you. Thank you for attending my talk.